Good morning. This is the third lecture on axial flow turbine. Contents of the lecture are stage efficiency of an axial turbine, total to total efficiency, total to static efficiency, and the turbine performance. Let me discuss now about stage efficiency. The aerodynamic losses in the turbine differ with the stage configurations, that is, the degree of reaction. An improved efficiency is associated with the higher reaction, which tends to mean less work per stage, and thus a large number of stages is required for a given overall pressure ratio. Thus, the understanding of aerodynamic losses is important to design the blading type, that is, whether one should use an impulse or a reaction stage for a particular application. Furthermore, the choice of blade shape, aspect ratio, spacing, Reynolds number, Mach number, flow incidence angle, tip clearance can all affect the losses and hence the efficiency of turbine stages. Please note that the two definitions of stage efficiency are in common usage. The choice between them depends on the application for which the turbine would be used. For many conventional applications, useful turbine output is the shaft power and the kinetic energy of the exhaust gas, that is Ct squared divided by 2, is considered as a loss. Hence, in this case, the ideal work would be Cp into T01 minus T3s, where T01 be the inlet total temperature and T3s is the ideal static temperature at exit, and thus a total to static turbine efficiency denoted as eta Ts based on the inlet and exit static condition is used. The ideal or isentropic and actual expansion process in a turbine has been illustrated in figure 8 here. Please note that the total temperature at inlet to the nozzle and the total pressure are denoted as T01 and P01. So that enthalpy is H01. So 01 be the state point at inlet to the nozzle. Thus, if I subtract from H01 C1 squared by 2, I'll get H1 and hence P1, which is the static pressure at entry to the nozzle. Now 1 and 3 be the expansion of gas in nozzle followed by the rotor. So 1, 2, the expansion in the nozzle, 2, 3, that of in the rotor. So P3 be the static pressure at the end of the stage. Now if I draw a isentropic line, I'll get a point, state point 3s, which is isentropic static temperature at the end of the stage. Now following energy equation in the stator and that of the rotor, I have marked now different state point. Suppose I know H01 must be equal to H02, so I have indicated the state point 02, and from H01 if I subtract C1 squared by 2, I'll get H1, Similarly, 802, if I subtract C2 square by 2, I'll get 2. And from the state point 2, if I add W square by 2, I'll get 0 2 relative. That hence P0 2 relative. And from state point 3, if I add WC square by 2, I'll get 0 3 relative and hence P0 3 relative. Similarly, from the state point 3, if I add C3 square by 2, I'll get 0 3 point and hence P0 3. Now note that the intersection of isentropic line from state point 1 to P03 is denoted by 03S. So 03S is the isentropic total temperature at the end of the stage. So thus please note that 3S denotes the static temperature and 03S is the total temperature at the end of stage or at exit of stage. Now considering this HS diagram and different precious lines along with the state points, now I can define eta Ts, which is the total to static efficiency, as T01 minus T03 divided by T01 minus T03S. Please note that here the efficiency is defined with respect to the static temperature at the end of expansion. Following equation 8, I can write eta Ts is equal to 1 minus T03 divided by T01 whole divided by 1 minus T3S by T01. Now T3S by T01, okay, this can be expressed in terms of pressure ratio P3 by T01. Thus I can write eta Ts is equal to 1 minus within bracket T03 by T01 divided by 1 minus P3 by P01 to the power gamma minus 1 by gamma. So equation 19 is an important relation which gives the total to static temperature. Now in some applications, particularly in turbojet engines, the exhaust kinetic energy is not treated as a loss, since the exhaust gas are intended to emerge at high velocity, which leads to thrust of the engine. The ideal work in this case is then Cp into T01 minus T03S. This is the T03S, rather than Cp into T01 minus T3S. Hence, this requires a different definition of stage efficiency, which is total to total efficiency and is denoted by eta Tt. Thus, I can express eta Tt as 1 minus T03 by T01 divided by 1 minus T03S by T01, where T03S is isentropic total temperature at the exit of the stage. Hence, eta Tt can be expressed as 1 minus T03 by T01 divided by 1 minus within the bracket P03 by P01 to the power gamma minus 1 by gamma. Thus the equation 20 denotes the expression for eta Tt. Now one can easily compare eta Tt and eta Ts by making an approximation as T03S minus T3S approximately equal to T03 minus T3. Thus I have told this part T03S minus T3s is equal to T03 minus T3. If we consider that, then this left hand side, that is T03s minus T3s, would be equal to C3 square divided by twice Cp. Thus now, using the equation 19 and 20, it can be easily shown that eta Tt equal to eta Ts divided by 1 minus C3 square within the bracket twice Cp into T01 minus T3s. Thus, eta Tt is greater than eta Ts. So we have concluded that total to total efficiency is greater than total to static efficiency. Now after definition, or after giving the expression for total to total efficiency and total to static efficiency, we can evaluate the actual turbine work as Wt is equal to eta Tt Cp T01 within the bracket 1 minus P03 by P01 to the power gamma minus 1 by gamma, or Wt is equal to eta Ts P3 into T01 within the bracket 1 minus P3 by P01 to the power gamma minus 1 by gamma. That means when total to total efficiency we'll use the total pressure ratio, and when total to static efficiency we'll use static to total pressure ratio. Despite of development in sophisticated computational method, accurate prediction of flow within the turbine passage, an estimation of stage loss and thus efficiency are still a matter of concern. Losses can occur due to the development of boundary layer on the blade surface exposed by centrifugal and coriolysis forces. Furthermore, the appearance of secondary flow, tip leakage vortices, inward boundary layer, south boundary layer contributes to significant amount of loss. Apart from that, there are effects of unsteady wax, that is, wax set by the adjacent row will interact on the boundary layer of the downstream blade, producing unsteady flow and loss. Furthermore, for transonic and supersonic blades, there will be shock boundary layer interactions, often contributing loss. In general, the cascade tests are performed for different blade configurations, and the correlations are established to evaluate the losses and efficiency on turbine blades. Now, with reference to the figure 8, that is, I have presented the figure 8 here, the effect of loss and thus irreversibility to the stator and the rotor blade are expressed by the difference in static enthalpies, that is H2 minus H2S and H3 minus H3SS respectively. Referring to the figure 8, please note that the state point 2 and the state point 2SS are denoted here. Similarly, the state point 3 and 3SS. Thus, the difference between this H3 and H3SS represents the irreversibilities in the rotor, and similarly difference between H2 and H2S indicates the irreversibility in the stator. Therefore, the non-dimensional enthalpy coefficient for the nozzle can be expressed as H2 minus H2S is equal to half C2 square into zeta n, where zeta n being the enthalpy loss coefficient for the nozzle. Similarly, the enthalpy loss coefficient for the rotor can be given as H3 minus H3SS is equal to half W3 square into zeta R, where zeta R being enthalpy loss coefficient for the rotor. After defining zeta n and zeta R, the expression for efficiency of turbine, that is eta TT and eta TS, can be approximated as eta TT is equal to within bracket 1 plus zeta R into W3 square plus zeta n into C2 square divided by twice H1 minus H3 whole to the power minus 1, and eta TS, that is total to static efficiency, is equal to within the bracket 1 plus zeta R into W3 square plus zeta n into C2 square plus C1 square divided by twice within bracket C1 minus C3 whole to the power minus 1. Thus equation 22 and equation 23 represent the expression of total to total efficiency and total to static efficiency in terms of zeta R and zeta n. With respect to earlier discussion, the turbine loss coefficient, which are denoted by zeta R and zeta n, are unknown. Thus here we have discussed about turbine loss correlations. A number of approaches have been made to predict the total pressure loss coefficient and the flow deviation angles of a turbine casket for an incoming flow. Here we'll restrict to the correlation of Söderberg in 1949. It is fair to mention that the method is quite adequate for making rapid estimations of turbine efficiency as per the study of Horlock in 1966. However, there is an error associated with the method, and the error over a range of Reynolds number is around 3%. However, the correlations are quite dated and are not expected to be adequate for modern highly loaded transonic turbine blade rows. Nowadays, these correlations may be used during the preliminary design of turbine. Indeed, a detailed casket testing or a computational analysis would always be applied for an accurate prediction of turbine blade losses. Thus, Söderberg loss coefficient can be expressed as zeta is equal to 0.04 within the bracket 1 plus 1.5 epsilon by 100 to the power square, where epsilon is the deflections, and for the nozzle epsilon is given by alpha 1 plus alpha 2, and for the rotor epsilons can be stated as beta 1 plus beta 2. Please note the following. While designing a turbine stage, often the restriction arises from the viewpoint of blade stress rather than the aerodynamics to achieve the maximum possible efficiency. In short, the blade speed is limited by the blade stress, particularly in high temperature application. Thus, often the blade speed is dictated by the maximum temperature at the inlet to the turbine and materials of the property used. Furthermore, turbine cooling is thus very vital, which determines the life of engine, particularly for a turbojet engine in aerospace applications. I'll now discuss on turbine performance. For a given turbine operating with a given fluid at sufficiently high Reynolds number, it can be shown through dimensional analysis that P02 divided by P03 is a function of non-dimensional mass flow rate and speed, which can be expressed as m dot root over r into T02 divided by P02 into d square and gamma d by root over gamma r T02. These are not truly non-dimensional. However, I can express P02 by P03 as a group of representative mass flow rate and the speed of the machines, where the state point 02 and 03 indicates the inlet and exit condition of the turbine. Now, using this equation, we have indicated the overall performance of a single stage turbine in the next slides. Figure 9a illustrates a typical characteristics of a turbine stage, eta Tt versus pressure ratio P02 by P03. Now I have plotted here eta Tt versus P02 by P03, that is pressure ratio, for different operating speeds. Now, if I consider the operating speed omega d by root over gamma r T02 as 0.75, indicates that even for high pressure ratio, say 0.4 per stage, it maintains a considerable high efficiency. Thereby, from this characteristics, one can say the per stage pressure ratio is higher here in case of a turbine as compared to that of compressor. Furthermore, the pressure ratio versus non-dimensional mass flow rate, that is m dot root over r T02 divided by P02 d square, has been plotted here for different non-dimensional speeds, that is omega d by root over omega r T02. It indicates that for any speeds after a certain mass flow rate, the pressure ratio lines becomes vertical. That means by increasing of pressure ratio after a certain mass flow rate, it does not increase mass flow rate. That means it has been choked. Thus, I have illustrated here the choking mass flow rate which occur at a pressure ratio corresponding to 3.5. Regarding performance of a turbine, it can be noted that the pressure ratio for a turbine is greater than that of a compressor stage, without sacrificing the satisfactory efficiency. The performance of turbines is limited principally by two factors. One is compressibility and other stress. The compressibility limits the mass flow rate through the turbine, and maximum allowable speeds limits the wheel speed. Furthermore, work done per stage, for example, depends on the square of the wheel speed. It should also be noted that the performance of a turbine depends very strongly on the maximum temperature. Of course, increase of maximum temperature limits the allowable speed of a turbine. Hence, while designing a turbine for suppose a turbojet engine, there must be a compromise between the maximum temperature and the maximum rotor tip speed. It should also be noted that for a given pressure ratio and adiabatic efficiency, the turbine work per unit mass is proportional to the inlet stagnation temperature. As an example, 1% increase of turbine inlet temperature can produce 2 or 3% increase of engine output. Thus, the inlet stagnation temperature of a turbine of modern aero engines is increased even beyond 2000 K, which is much beyond than the metallurgical limit. This is possible by advancement in technologies used for turbine blade cooling, and there are different advancements made. Different sophisticated technologies have been developed for turbine blade cooling. In this lecture, the stage efficiency, that is total to total and total to static, have been discussed. Furthermore, I have discussed on turbine performance. I have tried to say here that while designing the turbine stress is a parameter that to be considered, and sometimes stress is more critical than the aerodynamic considerations. Furthermore, I have indicated that the cooling of turbine blade is essential for its life. Thank you for listening.